Welcome to the 99th video in this series. In this video, we're going to make some improvements to how we're storing hash entries, and we're going to, with that, fix the problem that some people have mentioned over the years, and that is that we seem to have truncated principal variations in the output. I've compiled Vice and run it quickly here, doing the UCI and run commands that we have inside there. I stopped the search just as it hit depth 9, and you can see on depth 8 here that we've got a principal variation which is truncated. We only seem to have E2, E4, so the first move of the principal variation, and we haven't got the rest of the principal variation. And as I said, over the years, quite a few people have asked me why this is happening and is there an issue with the hash table. But before this video in preparation, I actually wrote some code printing the hash table out, so the entire thing where entries were stored, and I did things like check that every move that's stored, if it's not a no move, that it's actually a legal move for the position, everything was okay. And I did a load of other checking as well, and I'm pretty satisfied actually that the storing and retrieving of the entries is fine. The issue is another one. If we drop into search.c and the search position function, and I scroll down a bit, we've got this get PV line here. And as I highlight that, I see that we've actually got that twice, which is not very good, is it? So I'm going to delete that one here. I'm not sure why that's in there twice. Save that. So we get our PV line here, and this is what ends up being truncated. If we go and have a look at the get PV line function, I think that's at the top of PV table. Yeah, it is. It takes in the starting position, which is the position at the start of each iteration of the search. It probes a PV move. As long as this move is not no move, then what it does is try to make that move, and if it's able to make that move, then it makes the move on the board and it probes the next move from that position after the move is made. In other words, it uses the hash table to walk through the principal variation. If it finds a no move or an illegal move, then it just breaks out, takes the moves back that it's made, and then returns the count from there. The probe PV move is right down the bottom here. Here, familiar code, we just get the index in the hash table, and then we say that if we've got matching to our current key, then we'll return the move. So our probing of the hash table to get the principal variation is working. The actual problem is inside the store hash entry here. I'll paste some code in here. Please don't write this code because it's about to be deleted. I want to use it to demonstrate to you what we're talking about. What we've got here is some code that says, okay, we're storing a new hash entry. We'll get our index, which is our position key, which remember is an unsigned 64-bit integer, so very, very big, modulo the number of entries. Remember, we'll always have fewer entries than we have combinations of possible keys. What that means is we could get indexes that rub over existing entries in the hash table. And that's exactly what's happening and is causing the truncated principal variation. Here, this code is saying that if we're writing a new entry and the existing entry is greater than depth 8, so 9 or above, and the depth of the information that we want to save is actually 7 or below, then we're going to print the new hash key, so the position that's being sent in, the old key that's actually existing inside the table, the index that we're saving at, the depth that we're wanting to save, and the depth that we're replacing. So saving that and jumping back into the console, I'll clear the screen and recompile and rerun Vice. And when I rerun Vice, down at depth 9, you can see what's happening. We've got an old key here that was in the hash table, this 4C77. It had a depth of 9. So it was information right at the root of the principal variation. It was at this index. This new key gave exactly the same index, but information with a depth of 1, so very, very shallow in the search. And it rubbed over the entry that actually had information for depth 9. So what's happened at depth 8 here in the search is that it's entered E2, E4 because that comes from the root of the search. So the last thing we'll do is save that entry into the hash table because it's the actual best score for the list of moves. But whilst we're searching these moves through the iterative deepening, when we were one move into the tree, probably very early on, it already found and stored in the hash table the next move in the principal variation. Let's say that was D7, D5, like depth 7. So it will have stored that into the hash table, and it will have stored that with a depth of 7. More than likely, because this happened early on in the search, later during the search, right down at the leaves, there was an entry with depth 1 or depth 2 or something that rubbed over this entry. And therefore, when the search bubbled up, there's actually no entry with a correct move at the correct depth to follow on from the E2, E4. And therefore, the principal variation that we've extracted from the hash table becomes truncated because we've actually only got one move in there. So what we're going to do then is we're going to make some changes to the way we store the hash entries to avoid this issue that we've got. So we're no longer going to replace always. We're going to make some decisions. Now, if you look at the source code of other engines, much more complicated engines than Vice, you'll find there's some quite sophisticated algorithms for deciding exactly how to do the replacement. We're going to do it in a relatively simple way because this is meant to be a very simple engine to demonstrate the main techniques. The first thing you might think is, fine, we'll put some logic in like this, which essentially says if we're not at a deeper depth than the entry that's existing, then don't store something in the hash table. And this is okay, this will work. The problem with that is that as we go through the game, so as we make more and more moves in the game, we're going to end up with a hash table that is simply full of entries that are very, very old. And those entries are going to contain references and best moves from positions which are no longer relevant in the current position. So we need to find a slightly better way of doing things than that. And the way we'll do that is actually just by using age on the hash table. If you imagine that in terms of a very simplified version, imagine we have a hash table with 3 indexes, so indexes 1, 2, and 3. And then we make our first search. We store an entry in that search of depth 5 and the age will be 1. So at the start of the search, the age will be 1. So this entry at index 1 is depth 5, age 1. Then we do the next search and we store an entry this time at index 2. We don't overwrite anything or anything like that, but in that search we've stored an entry at index 2, but that entry now has depth 5 as well, but its age is 2. Then, I'm sure you can spot the pattern here, we do the next search, so we're now 2 moves into the position, we're searching the position after 2 moves we've made. The age of the entries in the hash table will now be 3, and we've stored one now at index 3, so we haven't overwritten anything that's already existing, and again depth 5, but the age of the entry this time is 3. Now we do our depth 4 search, and when we come to our depth 4 search, we want to store an entry at index 3, but the depth we've got is shallower. It's shallower than depth 5. However, the age that we have is greater, so we know that this contains newer, more relevant information, even though the depth is shallower than the previous entry at search depth 3. Now, of course, you could do something a lot more sophisticated this, and some engines do. We're going to keep it simple like this. Therefore, this entry here is green because we are able to store it, because even though the depth is shallower, we've got a newer entry because the age is greater. If we continue in search 4, and then we find that we've got another entry to go in at index 3, but this entry only has a depth of 1, then we'll check the age and we'll see, well, it's got the same age as the entry that's already there. Therefore, we're not going to overwrite it and it's going to stay red, because we know that the information we've stored is as new as the information that we want to store, but the depth is greater, therefore it's better information for the hash table. And it's this principle here that we're going to update in the code to hopefully sort that truncated principal variation problem out. And actually, what I've seen from doing some testing, it does give us a small gain in performance from the engine as well. So back inside the code then, into defs.h, where we have our structure for the hash entry, we'll type here int age. So we'll actually store the age information, and then for the hash table also we'll make current age as well. Now I've added those in, I'd like to jump into pvtable and find our clear hash table here. And what we'll want to do here is we'll have the table entry age is equal to 0. And then also below this new right here, we'll do the current age is equal to 0 as well. Now, one thing that's critical now is that we're able at the right time when using the program, or other people use the program, to reset the actual age of the hash table. So the way we'll do that is using the UCI new game command. So inside UCI.c, we have this UCI new game here. And according to the protocol, and I've been back and double checked, this is the command that will be sent before we start any new game. So we can use this new game to make sure that we clear the hash table. So what we want to do inside here then is, before we pass the position, we'll clear the hash table, and inside there we want to send in our now global hash table. Now we can go back into pvtable and into store hash entry, and here we can make use of our new age and add in a little bit of logic here to try and improve things. So below the asserts here, I'm going to type int and replace is equal to, I'll put our false, which you remember is a definition effectively a 0. And now here, where we're writing something new, we can put replace is equal to true, because we're definitely going to want to replace here because there was actually nothing existing in the hash table, so it doesn't matter what we have. Otherwise, what we want to do is put some logic in here to use the depth and the age. What I am going to do is delete this overwrite. I'm not really interested in these statistics at the moment, and we'll fix those later on in the series. For now, I want to get the actual saving of the entries correct. So what we're going to say here then is we're going to say that if the table pointed to table at the index.age is less than the current age, so if the entry that we're trying to replace is older than our current entry, then we can replace. Or if the entries are the same age, then what we want to do is check for the depth. So what we'll do is we'll say that or the table dot depth is less than the depth that we're trying to store, then we can set replace is equal to true. So once we have that, we can be sure that we're only going to override an entry if we've got a newer search than the entry that's already in the table, or we've got a deeper entry than one that was already stored on this search. So what we can say here then is that if replace is equal to false, then we'll just return. Otherwise, we can drop down and add the age to the entry, and then go into search.c, and inside the clear for search, we'll make sure we increment the hash table age. And now we can save, drop into the console. Over in the console then we can compile Vice and run the program. So we'll type UCI and run, and I'll go to depth 10 here. You can already see we're getting very nice principal variation here with no truncation whatsoever. I'm going to hit stop and actually do run again. And okay, we've got very nice PV coming out of there. I'm going to hit stop and do run again because our replacement scheme is still not perfect for extracting the PV. It's still okay here actually, so I'm going to do stop and run again because sometimes, there we go. Okay, now we're getting slightly truncated PVs. So it's still not perfect, but it's a lot better than it was, and also for performance of the engine, it's going to give us a little bit of a gain as well. So we have an improvement for how the PV is printed. And we've also managed to, inside the code, to add a little bit of logic to improve the way our hash table performs as well. So we're storing more relevant and deeper information than we were before. Now we've done that, we're able to finally move on to looking at making an input thread and removing all of the input polling.